In this example, we are given 0.100 molar acetic acid solution. We're also given its acid ionization constant, which is 1.8 times 10 to the power of -5. We are asked to find the hydroxide ion concentration, the hydronium or H plus ion concentration, the pH, the pOH, the pKa, the pKb, and percent ionization or percent dissociation. Now, since we're dealing with a weak acid, acetic acid, we are going to use the ice table approach. So first we have our acetic acid. Acetic acid in water will dissociate into CH3, COO- and H3O+. Now we write down our initial conditions. We're given 0.100 molar acetic acid. Water is not participating in this reaction. Then we have 0 molar of CH3 COO-, and we have 0 molar of H3O+ ions. Next, we write down our change conditions. So we have negative X for CH3 COOH, positive X for CH3 COO-, and positive X for H3O+. Similarly, for equilibrium, we're going to get 0.100 minus X for CH3 COOH. We have X for CH3 COO-, and we have X for H3O+ or H+ ion concentration as well. Now the next thing we do is that we use our acid ionization constant, which is Ka. We know that Ka is equal to concentration of CH3 COO-, which is a part of the product, and H3O+ concentration over a reactant concentration, COOH. That is equal to 1.8 times 10 to the power of -5. We can plug our equilibrium expressions in to get x squared over 0.100 minus x is equal to 1.8 times 10 to the power of -5. Now, since 10 to the power of -5 is less than that of 10 to the power of -4, we can use the 5% rule, or we can use the 100 rule. It's the same thing, and we can ignore this negative x. Now, since we're using the 5% rule or the hundreds rule, we're getting rid of the x over here. We can say that x squared over 0.100 is equal to 1.8 times 10 to the power of -5. Now, solving for x, we get a value of x equal to 1.3 times 10 to the power of -3 molar. Now, before we plug our value of x back into each of these equilibrium expressions, we need to validate whether we are on the right track or not. So we have our x. So for validation, we have our x, and initially we started with 0.100 molar of acetic acid, times it by 100%. So we have 1.3 times 10 to the power of -3 over 0.100 times 100%, and that is equal to 1.3%, which is less than 5%, so we are correct, we are on the right track. And we can plug the value of x back into all the equilibrium expressions to get what we want. We want the concentration of H3O+ ions, or H+ ions the most here, because that's what's asked in the question. So therefore, the concentration of H3O+ ions is going to be equal to X, which is equal to 1.3 times 10 to the power of negative 3 molar. Now, since we know the H plus or H3O plus concentration, we can get our pH. So we can say that pH is equal to negative log of H3O plus or H plus. So it's going to be equal to negative log of 1.3 times 10 to the power of negative 3, and that is equal to 2.89. Now that we have the pH and the H3O plus ion concentration, we can figure out the OH minus concentration as well as the POH. Now we know that pH plus POH is equal to 14. Therefore, our POH is going to be equal to 14 minus pH, which is 14 minus, we know that our pH is 2.89, minus 2.89, and we end up with a POH of 11.11. Now, we have almost everything. We just have to find our pKa, pKb, and percent ionization. We know our Ka is given, so Ka is equal to 1.8 times 10 to the power of negative 5. And we know that pKa is equal to negative log of Ka. So that is going to be negative log of 1.8 times 10 to the power of negative 5. And that will give us a pKa of 4.74. And just like before, we know that pKa plus pKb is equal to 14. Therefore, our pKb is going to be equal to 14 minus pKa. We already know our pKa as 4.74, so it's going to be 14 minus 4.74, which is equal to 9.26. Now that we have almost everything, we only have percent ionization left to find. Now, percent ionization is just like percent validation, but the concept is different here. Now, percent ionization is equal to the ratio of the acid or weak acid that has dissociated already with respect to the acid amount that we started with in the beginning. So the amount of acid that dissociated was 1.3 times 10 to the power of negative 3, and the amount we started with initially was 0.100 molar. And we times it by 100%, and we get a percent ionization value of 1.3%. So we get a percent ionization value of 1.3%. That's how much has dissociated over the entire reaction. Now for part B, which is very similar, we have 0.200 molar ammonia solution, and we are given our base dissociation constant, Kb, of 1.8 times 10 to the power of negative 5. Just like before, we're going to start off with a reaction. So we have NH3, which is a weak base, in water, dissociating to give us H3O plus and NH2 minus. Now we note down our initial conditions, so we have initially 0.200 molar of NH3, and everything else is 0 because they're not there. The change is going to be negative X for NH3, positive X for H3O plus, and positive X for NH2 minus. Then for equilibrium, we're going to get 0.200 minus X for ammonia, X for H3O plus, and X for NH2 minus. Next we use our base dissociation constant, so we have Kb equal to H3 plus times NH2 minus over NH3. We plug our values in. We get 1.8 times 10 to the power of negative 5, which is our Kb value, is equal to x squared over 0.200 minus x. And now since we know that 10 to the power of negative 5 is less than that of 10 to the power of negative 4, we can go ahead and use the 5% or 100 rule to eliminate this x. So next we have x squared equal to 0.200 times 1.8 times 10 to the power of negative 5. Taking square root, we get our x value as 1.897 times 10 to the power of negative 3 molar. Now that is exactly the concentration of our H3O plus ion. Now we already have our H3O plus ion concentration, so we can figure out the pH. Our pH is going to be equal to negative log of H3O plus ion concentration, which is going to be equal to negative log of 1.897 times 10 to the power of negative 3, and that is going to be equal to 2.72. Now that we know the pH, we can figure out the pOH. So pH plus pOH is equal to 14. Therefore, pOH is going to be equal to 14 minus pH, which is equal to 14 minus 2.72. And that is going to be equal to 11.28. Since we have the pOH, we can now figure out the concentration of OH minus ions. So OH minus ions concentration is going to be equal to 10 to the power of negative pOH, which is equal to 10 to the power of negative 11.28, and that is equal to 5.25 times 10 to the power of negative 12 molar. Now that we know the concentration of our hydroxide ions and the concentration of our H3O plus ions, pH and pOH, we can now move on to figuring out the pKb and the pKa. So we are already given our Kb value, which is 1.8 times 10 to the power of negative 5. So we can use that to find our pKb value. So pKb is going to be equal to negative log of Kb, which is negative log of 1.8 times 10 to the power of negative 5, and that is equal to 4.74. Now we can use that to find our pKa, so pKb plus pKa are equal to 14. So pKa is going to be equal to 14 minus pKb, which is equal to 9.26. Now if we look carefully, we used 0.200 molar ammonia in the beginning, and we ended up with a hydroxide concentration of 5.25 times 10 to the power of negative 12. So we can use these two values to figure out how much has dissociated, or how much of ammonia has dissociated in this entire process. So initial ammonia concentration was 0.200 molar. Amount of ammonia or concentration of ammonia which dissociated to form hydroxide ions is equal to 5.25 times 10 to the power of negative 12. Now, a percent dissociation or ionization value is going to be equal to 5.25 times 10 to the power of negative 12 over 0.200 times 100%. That will give us a final value of 2.625 times 10 to the power of negative 9%. Now, there's nothing to panic about this because naturally ammonia tends to not dissociate at all. So most of the time, even though it's dissociating, 99% of NH3 usually stays NH3. So we are still on the right track and we have found everything that we were asked to find. Let us now move into a different example.